Our solar system is a place of wonders. It's filled with diverse and fascinating worlds. Among these are the icy moons and dwarf planets located far from the sun. These celestial bodies may seem cold and lifeless at first glance, but beneath their frozen surfaces lies a secret. These bodies have the potential to harbor vast hidden oceans. These oceans are larger than any on Earth. These subsurface oceans, as they are known, are a tantalizing area of exploration for scientists. They offer a unique opportunity to study the potential for life beyond Earth. These oceans remain liquid despite the frigid temperatures of the outer solar system. This is due to a combination of factors. These factors include tidal forces from nearby gas giants and internal heat generated by radioactive decay. These hidden bodies of water represent a new frontier in our understanding of the universe. They challenge our assumptions about where life might exist. The search for life beyond Earth has just gotten a whole lot more interesting. Subsurface oceans, as their name suggests, are bodies of water located beneath the surface of a planet, moon, or dwarf planet. Unlike surface oceans, which are exposed to the vacuum of space, subsurface oceans are protected by a layer of ice, rock, or both. This ice shell can be tens or even hundreds of kilometers thick. This makes them incredibly difficult to detect and study. The water in these oceans is not frozen solid despite the extreme cold. This is because of the internal heat generated by the celestial body as well as tidal forces from nearby objects. This heat keeps the water in a liquid state. It may even create hydrothermal vents on the ocean floor. These vents could provide the necessary energy and chemicals to support life. The existence of subsurface oceans in the cold depths of our solar system might seem counterintuitive. After all, water freezes. How can these oceans remain liquid beneath kilometers of ice? The answer lies in a delicate balance of internal and external forces that provide the necessary heat. One of the most significant sources of heat is tidal heating. This phenomenon occurs due to the gravitational interaction between a moon and its host planet. The gravitational pull of the planet isn't uniform across the moon's entire diameter. This uneven pull creates friction within the moon's interior. This friction generates heat, much like rubbing your hands together generates warmth. This heat can be substantial enough to melt ice and maintain a liquid ocean beneath the surface. Europa, a moon of Jupiter, is a prime example of this phenomenon. Another vital heat source is radioactive decay. Many celestial bodies contain radioactive elements within their cores. As these elements decay, they release energy in the form of heat. This heat contributes to the internal temperature of the moon or planet. Over billions of years, this heat can accumulate and become significant enough to melt ice and form a subsurface ocean. This process is thought to be crucial for maintaining the subsurface ocean on Saturn's moon Enceladus. Our solar system harbors celestial bodies that may host subsurface oceans. These range from moons to dwarf planets, each unique. Europa, Jupiter's moon, is a famous candidate. Its surface has fractures, hinting at a subsurface ocean. Enceladus, a moon of Saturn, is another contender. Cassini revealed water vapor plumes from its south pole. Titan, Saturn's largest moon, has lakes and rivers of methane. Beneath its surface, a water-ammonia ocean may exist. Ganymede, the largest moon, shows evidence of a subsurface ocean. Callisto, another of Jupiter's moons, may harbor a deep subsurface ocean. Triton, Neptune's largest moon, has geysers suggesting a subsurface ocean. Pluto, once the ninth planet, may also have a subsurface ocean. Section 5. Seeking the unseen. Evidence of subsurface oceans. Detecting subsurface oceans on distant celestial bodies is no easy feat. These oceans are hidden beneath kilometers of ice and rock. Scientists use methods like magnetic induction and gravitational analysis. Magnetic induction reveals subsurface oceans on moons like Europa. Gravitational analysis helps study Ganymede. Cassini found definitive proof of a subsurface ocean on Enceladus. Section 6. Oasis in the darkness, the potential for life. The discovery of subsurface oceans in our solar system has profound implications for the search for extraterrestrial life. These hidden water worlds, shielded from the harsh conditions of space, offer a potentially habitable environment where life could emerge and thrive. One of the most promising aspects of subsurface oceans is the possibility of hydrothermal vents. These vents, found on the ocean floor, release heat and chemicals from the moon or planet's interior. On Earth, hydrothermal vents support thriving ecosystems, even in the absence of sunlight. These ecosystems rely on chemosynthesis, a process where microorganisms convert chemicals from the vents into energy. The presence of hydrothermal vents in subsurface oceans could provide the necessary energy and nutrients to support life. The combination of liquid water, organic molecules, and a source of energy makes these vents prime candidates for the existence of extraterrestrial life. While we haven't found definitive proof of life in these oceans yet, the possibility is tantalizing and drives further exploration. Section 7. Journeys into the deep, future missions and their challenges. The tantalizing possibility of subsurface oceans teeming with life has spurred space agencies worldwide to plan ambitious missions to these distant worlds. These missions aim to study the composition and structure of these oceans, search for signs of the life, and ultimately answer the question, are we alone in the universe? One such mission is NASA's Europa Clipper, scheduled to launch in the 2020s. This spacecraft will orbit Jupiter and conduct multiple close flybys of Europa. It will use a suite of instruments to study the moon's icy shell, map its subsurface ocean, and search for plumes of water vapor erupting from the surface. The data collected by Europa Clipper will help scientists better understand the habitability of Europa's ocean and pave the way for future missions. Another ambitious mission is the European Space Agency's Jupiter Icy Moons Explorer, or JUICE. JUICE will explore 3 of Jupiter's largest moons, Ganymede, Callisto, and Europa. It will study their atmospheres, surfaces, and subsurface oceans, searching for signs of life and unraveling the mysteries of these icy worlds. These missions, while groundbreaking, face significant challenges. The extreme distance to these moons requires powerful rockets and long travel times. The harsh radiation environment around Jupiter poses a threat to sensitive spacecraft electronics. Developing instruments capable of penetrating the thick ice shells to study the subsurface oceans is a daunting technological hurdle. Section 8. Plumbing the depths. Technological hurdles in ocean exploration. Exploring subsurface oceans hidden beneath kilometers of ice and rock presents unprecedented technological challenges. Overcoming these hurdles is crucial for unraveling the mysteries of these hidden worlds and searching for signs of life. One of the primary challenges is developing probes capable of withstanding the extreme pressures and temperatures found in subsurface oceans. These probes must be robust enough to penetrate the thick ice shell without being crushed or malfunctioning. They must also be equipped with sensitive instruments to collect data on the ocean's composition, temperature, and pressure. Another challenge is developing communication systems that can transmit data from the depths of a subsurface ocean back to Earth. Radio waves, commonly used for communication in space, are attenuated by water and ice, making them unsuitable for this purpose. Scientists are exploring alternative methods, such as acoustic communication or using fiber optic cables to relay data to a surface lander, which can then transmit the information back to Earth. Perhaps the most daunting challenge is developing technologies for life detection in these extreme environments. Traditional methods for detecting life, such as searching for organic molecules or evidence of metabolic activity, may not be suitable for the subsurface oceans. These environments could harbor life forms vastly different from those on Earth, requiring innovative approaches to life detection. Section 9. A universe of possibilities. The significance of subsurface oceans. The discovery of subsurface oceans in our solar system has profoundly impacted our understanding of the universe and our place within it. These hidden water worlds, once confined to the realm of science fiction, are now a tangible reality, expanding the horizons of exploration and challenging our preconceived notions about where life might exist. The study of subsurface oceans is not merely about finding extraterrestrial life, it's about understanding the limits of life itself. By studying these extreme environments, we can gain insights into the conditions necessary for life to arise and thrive, both on Earth and beyond. Subsurface oceans also provide a unique opportunity to study the geological and chemical processes that shape planetary bodies. By analyzing the composition of these oceans, we can learn about the formation and evolution of moons and planets and gain a deeper understanding of the solar system we call home. The discovery of subsurface oceans has ignited our collective imagination, inspiring us to reach for the stars and explore the unknown. These hidden water worlds, with their potential for life and their scientific treasures, beckon us to embark on a journey of discovery that promises to reshape our understanding of the universe and our place in it.